Okay, so I just wanted to discuss some of the recent changes to our National Seismic Hazard Map. We've been working on these maps for the last 4 or 5 years. We released the maps in 2008 in conjunction with the release of the NGA equations and also with the new CEA models for California, which were released to the public also at the same time as our map. So we've had a lot of information that we felt like was important for us to incorporate in the new maps. And today I just want to discuss some of these changes that were made, and especially how they were incorporated with the NGA equations. So you probably are aware that there are lots of different levels of hazard across the United States. And for the next few talks, we're going to talk about how the design maps for the United States were developed. And so I want to just introduce you to some of the features. Of course, you're very familiar with the effect of the Cascadia subduction zone along the coast, but we also have a number of crustal faults in California and the Intermountain West and the Pacific Northwest that contribute a lot to the hazard. And so there are different attenuation relations applied to the crustal faults and different ones to the subduction zone earthquakes. And we'll be discussing a little bit about that. But it causes a high hazard in the western U.S. from all of these different effects. We also have different places around the U.S. like the New Madrid area where we had some great earthquakes back in 1811, 1812. We have large earthquake that occurred in Charleston, South Carolina, some up in Canada, in particular that affect the northern part of New York and up in the northeast part of the United States. You're familiar with the subduction zone that comes across the southern coast of Alaska. And then, of course, we have the volcanic hazard in Hawaii that we've been discussing. But today I want to focus primarily on the conterminous United States and some of the changes that were made in that area. So we went through this big process. Probably several of you were involved in some of these meetings. We held one regional workshop in downtown Seattle here where we discussed a lot of the details of how we wanted to, in particular, model the subduction zone. So we looked at all the different subduction zone models. There were debates about, is there clustering on the subduction zone models? Do they occur more often in the southern part of the subduction zone rather than in the north? I'll show you what we ended up doing a little bit later, but for this slide, I just want to show you that there were 4 regional workshops that were held across the country and 2 workshops on attenuation relations, one for the central and eastern United States and one for the NGA equations. We also held a workshop for the users, the National User Needs Workshop, in which the engineers had a chance to really give us feedback on what they would like to see in these maps and how these could be applied to the design maps. Now, there were 2 external review panels that we held. One was what we called the Tiger team that Yusuf just talked about. And in particular, in this workshop, in this group, we wanted to ask the modelers, do you think that these models that include earthquakes like the Taiwan earthquake and the earthquakes in other places in the world, do these apply to the western United States? Can we use these to confidently model crustal earthquakes in the western U.S.? And the answer to that was yes. They felt like they did. But they did a lot of work to try and show us these residuals that Yusuf talked about to try and convince us that there wasn't a bias, that these data from other parts of the world weren't biasing the data for the United States. So in the end, this Tiger team concluded that the data that was being given by NGA was sufficient and complete for us to use in our national maps, and we have used them. We also had a review panel just to give us advice on the different ways of modeling, and we had these various draft maps and quality control factors. So in the end, again, we released these back in April of 2008, and they are now on our website. So what I want to do now is go over different parts of the United States and just talk about some of the biggest changes. I don't have time to go into detail on any of these, but if you have questions, please feel free to get a hold of me and ask me questions later, or you can send me an email. Some of the biggest changes in the central and eastern United States were that we had a new analysis of magnitude distribution for earthquakes all the magnitude uncertainties that are built into the catalog cause some biases in the rates that are applied. So we tried to account for those. For the New Madrid, where we had those big giant earthquakes, we felt like we needed to revise some of the temporal and spatial models. So we've changed a couple of the recurrence relations for the New Madrid zone. We've added a temporal cluster model. Also, we revised a little bit of the Charleston, South Carolina zones to account for some of the structures that were observed offshore, just off the coast of South Carolina. We really don't know where those earthquakes occurred exactly. And so we look at all the candidate structures, faults in the area, and try and determine where we feel like the best area for a future earthquake might be. And one of the biggest changes was that in the central and eastern United States, as in the NGA equations, there were some big changes to the attenuation models that caused some big changes to the hazard maps. I want to just show you real quickly a slide by Gail Atkinson, in which you can see that we have typically used, if you look at the distance from the rupture on the x-axis and the Fourier amplitude on the y-axis, you can see that the black line represents what we have typically used to model the attenuation or the fall off of ground motion with distance. And you can see that the data that Gail has shows that it falls off more steeply. So these are very important aspects, and in fact, they're so important that Yusuf and I and others are beginning a process of doing an NGA East now. We're beginning the NGA East so that we can study some of these factors to try and make these relations better in the future. But the impact of that was pretty severe. You can see in this is all the different attenuation models, again, with Joyner bore distance on the x-axis and the 0.2 second spectral acceleration on the y-axis. And the ones that I want to really point out are the two blue curves on there. AB95, you can see up near the top, and AB05, which is their new 2005 model that incorporated this faster fall off at distances beyond 75 kilometers. And you can see that these ground motions for that particular relation have been reduced by about a factor of 2 or more. So this again has brought down the high frequencies, the 0.2 second spectral accelerations in the east. Now I'm going to turn my attention to the west. We're going to talk about the different attenuation models in the west. Now, in particular, in this conference focuses on the NGA equations. And so Yusuf showed something similar to this, but this is an example for a magnitude 7.5 earthquake at 1 second spectral acceleration. The red curves represent the new NGA equations, and the blue curves represent what we used before. So for the crustal faults in our model, you can see that at many distances, almost all distances, for this particular magnitude, the ground motions have come down. Now, Yusuf also pointed out that there are places when you have hanging wall effects and other things that you can actually increase the ground motions with respect to others. In general, though, this will be the trend that you'll see in the western U.S. when we get to our ratio maps. It also applies to normal faults, and we won't go into details on that. So for the Pacific Northwest, I think, again, most of you are aware that we have a lot of information on the size of the biggest earthquakes in the model. So we have trees that died that are along the coast. We can look at the tree rings that are developed by that in the slide just in the lower corner here, where they all seem to die at about 1700. We also have data of large tsunamis affecting the coast of Japan that were recorded back in 1700 in Japan, and when they dig trenches along the coast, along the coast of the Pacific Northwest, they see these tsunami layers. So this is the data that's used to indicate that there was a large earthquake on about January 27, 1700. And the debate now is, how do these earthquakes occur? In our previous models, we used a magnitude 8.3 to represent some smaller individual segment ruptures, and a magnitude 9 to represent the full rupture from northern California up to northern Washington. And now again, people are starting to look at some of this data and trying to understand it, interpret whether there are other models that should be considered. In what we did in 2008, was we decided to account for the complete range from 8 to 9. So we modeled a Gutenberg-Richter from 8 to 8.7, and then we have a characteristic model, magnitude 9, with some uncertainty that encompasses the rest of the magnitude range. So we've accounted for all the potential earthquakes between 8 and 9, probably 0.2 on the high end. So that's one of the major changes along the coast. And these are the major changes then to the Pacific Northwest region. We have a new Cascadia subduction zone magnitude frequency distribution that we just talked about. We added a Portland, Oregon deep zone. We found that there were some deep earthquakes in the area of Portland that seemed to also indicate that there might be some kind of a deep action that's going on there. And so we've applied a rate to that area that's near Portland on the coast. And then we have these, we added 3 new crustal faults to the area, mostly in Washington state. And we also have applied some new subduction zone attenuation models. So I want to show you a little bit about these models. Now, they're not the NGA models, but they're important for the state of Washington and Oregon. So in this figure, you can see that all the different attenuation models that we considered. In the past, we've used the Atkinson and Bohr, shown in red, for a subduction zone 8.3 and 9. We used the geomatrix that Bob Young's developed. He'll be talking later, magnitude 8.3 to 9. And we used to use another relation by Sadig, 8.3 to 9, that geomatrix recommended using along with the geomatrix equations. So we used to apply that. Now, with these new equations, we adopted the Zhao attenuation relations, which is a newly published subduction zone model. You can see that the Zhao attenuation model is higher for the magnitude 9 in particular. It's similar to the Sadig model for magnitude 8.3, but it's higher than the Sadig for the magnitude 9s. And it decays a little faster than the Atkinson and Bohr and the Young's model. So at distances out beyond 150 kilometers, say. So those are the models. What we did was we adopted the Zhao et al. Model and didn't include the Sadig model in this current version. Now, this shows, again, the effect of the 9.0 Zhao, the 9.2 Zhao interface, and a 9.0 that we would use from Sadig. And you can see that the 2 black curves of Zhao are higher by a significant factor than the Sadig model was. And so C.B. Krause, who's also one of the speakers, suggested that we look at the Takachi-Oki data to try and verify that this really was a model that we should be considering. And you can see that the Takachi-Oki data is shown mostly for rock sites. And you can see our rock sites for the Zhao attenuation relations for an 8.3 and a 9. Of course, the Takachi-Oki is an 8.3. And you can see that in particular, there are some high ground motions in the region of less than 100 kilometers that the Zhao model is modeling probably similar or in the range of what the others were, at least what the Sadig model was in the past. So we felt more confident that maybe this was a model that we should be considering, that maybe a subduction zone earthquake might really cause some higher ground motions than some of the other relations that we have. Okay, I'm going to quickly go over some of these other areas. Just the Intermountain West, we had a WSPIC, the Western States Public Seismic Policy Council, gave us some advice on what to do for faults in those regions. Those are mostly normal faults, and they thought we should account for uncertainties in dip. We applied a magnitude frequency distributions similar to the way we had in California, and we are trying to account for some geodetic data there. The geodetic data is a new data set that's becoming very useful to us. We've got 10, 15 years of good geodetic data, and we would like to start making source models based on this geodetic data. In addition, we have working groups that were set up in Utah and Nevada that give us slip rates, and we've accounted for some larger earthquakes on the Wasatch Fault. I should mention that there's also a working group that's been established in the Pacific Northwest as well that's giving us advice on what new faults to include in future models. And then the other big one, again, is the next generation attenuation relation. And there are some details in faulting that I don't have time to go into, but we are trying to look at this geodetic data. Now, we want to be able to develop in the future models that are consistent with this. And through much of the region of the western United States, the geodetic data is significantly higher than the corresponding geologic data. So what we've looked, when we have geologists dig trenches and we compare that to what we see the strain rates are across the western United States, it seems like in many cases the strain rates from the geodetic data are higher than the strain rates than we would predict from the geologic data. So we're trying to take these into account. It's not an easy thing because we don't know exactly what that geologic or geodetic data really represents. So we're trying to understand, what are these discrepancies? Are we missing events in trenches that the geologists are digging? And is the geodetic data representing more than just strain that's taking place in earthquakes? Is it representing other kinds of strains that's more aseismic? So these are the questions. We've held some workshops on this. We're trying to understand it. In the Pacific Northwest, we also have a geodetic type of zone in the Seattle area to account for earthquakes that we might not recognize. Maybe we haven't recognized all the faults. The LIDAR data in the Pacific Northwest is helping us a lot to identify many of the structures that we had missed previously, but we do know that we've missed some of these faults that could be seismogenic, and we want to take these into account. So this is the future, and we've used this in the past to kind of try to estimate where some of these future earthquakes might occur. Finally, we have the USURF model in California. This was a model that was built by a large group of people in California. We separate the faults into type A faults, in which we typically do time-dependent analysis for. These A faults have a lot of parameters that have been well defined. They've been used in working groups to establish the rates and probabilities of earthquakes in 30 years. And so we separate those and use a slightly different model to account for those. The B faults are all the other faults that have been modeled. And some of those aren't quite as well constrained, but people have identified Holocene events on each of these different structures and published information on that. Now, one thing that we've tried to always do is use we've tried to use published information wherever we could. People are trying to discuss now whether we should be going to a more formal process to try and evaluate all this data, but right now we're just trying to establish these models based on published information that's available to the public. We also have these C faults, which are the zones that you can see in green up here. Those are zones that are established primarily from that geodetic data that I showed you a minute ago. What they came up with for California was that there's more than a 99% probability in the next 30 years for more than one earthquake of 6.7, which is the size of the Northridge earthquake. So there's a very high probability that you're going to have a Northridge type earthquake in any 30-year period. And this was, again, delivered to the public almost the same day as our new national maps were. And we used this information in establishing the new national maps. There was a scientific review panel of many individuals across California that participated in this. And essentially there were new fault models, especially for the San Andreas fault system, that were developed as part of this effort. So let's talk a little bit now about how these NGA equations, how the subduction zone equations, and how the central and eastern U.S. equations have affected the hazard across the United States. This plot, I hope you'll be able to read some of it, but I wanted to include it so that maybe you could look at it in your books and see these. But you can see that I've tried, and you won't be able to see this on yours because they're not color, but in red on the right side shows the ratios of the 2008 to the 2002 hazard. And if it's red, then it represents a greater than 10% change in the hazard. So you can see that in Southern California, in general, the hazard is lower. This is for 1 second spectral acceleration, which is where NGA has its largest effect. The ground motions in Santa Barbara are a little higher, and that's mostly because of the sources that were considered, that were changed in the Santa Barbara Channel. If you look at Northern California, all of them are slightly smaller than the previous version, and this is all essentially because of NGA. For the Pacific Northwest, Seattle is a little lower, about 12% in this case, and that's mostly because of NGA, because of crustal faults. The crustal faults dominate a lot of the hazard in the Seattle area. We have the Seattle fault, some of these other faults but when you look at the subduction zone, like you are in Portland, the ground motions have come up because the ground motions are higher with that new Zhao attenuation relation. In the Intermountain West, again, the ground motions are lower for 1 second, and in the central and eastern US, they're a little lower, but if you look at the higher frequencies, the 0.2 seconds, the ground motions are lower because of that new Atkinson and Bohr attenuation relation, primarily. So these are the hazard spectra for 2002 versus 2008, and as I'd mentioned, Seattle is slightly lower than it was in 2002, primarily because of the new NGA attenuation relations. If we were to look at Portland, Portland again would be higher because of the Zhao et al. Attenuation relations. And you can see that in general, especially at 1 second and the longer periods, there's a significant factor of about 30+% decrease in the ground motions in 2008 compared to what they were in 2002. Same story in the eastern United States, where you have Paducah and New York City. The 2002 model is higher than the 2002 model is higher than the 2008 model. So when we look at ratio maps, and Yusuf showed a couple of these, for the 5 hertz, which is where the Atkinson and Bohr attenuation relation affected the ground motions most, you can see that in many places in the central and eastern US, the ground motions are down 20%. Because of the cluster model in New Madrid, the ground motions are more mixed, and you can see the effects of that. And for 1 hertz, you see a similar pattern, but not as severe. These are down 10 to 15%. When you look at the 5 hertz for the western US, you can see that along coastal Washington State and Oregon State, the ground motions are higher than they were by about 10, 20, maybe even up to 30% in some places because of this new Zhao et al. Attenuation relation. In other places, these are more similar. There's some places that are higher, some places that are lower. When you look at the 1 second, which is the primary impact of the new NGA equations, you can see that these ground motions are down 25, 35% in all those blue areas across the western US. In the Pacific Northwest, the ground motions are a little higher again because of the Zhao et al. Attenuation relation. I just want to mention, because my time is running out, that we have developed other maps for other periods now that we hadn't had originally. So we have 10 hertz and 2 seconds. You can see the effect of those ratios again, where the ground motions are higher in the Pacific Northwest at both 10 hertz and 2 seconds due to the Zhao et al. Attenuation relation primarily. When you're up in Seattle, they're more similar because you have the effect of the crustal faults in that area. I want to talk just a little bit because NGA has given us all some new estimates of ground motions for different site conditions. So Yusuf had mentioned the VS30 model. And in this plot, I'm showing for the Cho and Youngs, the blue curves are the green, red, and blue curves represent the range of amplifications that are taking place in the D site category of NEHRP. So this is between 180 and 360 is D. And you can see these are the curves that represent the types of amplifications that are taking place. And in the black curve, you can see what's used in the current NEHRP design for amplifications. So for 5 hertz, again, you can see that for most places, the amplification using the Cho and Young's relation tends to be slightly lower than many of the factors that you would have applied if you just chose to use the NEHRP factors. When you get to very small ground motions, however, less than about 0.4, 0.3, there's an amplification compared to NEHRP. If you look at 1 second, it's more of a mixed bag where some places are higher, but if you look at 0.5 to 1 G spectral acceleration, the ground motions are amplified slightly more than they were with NEHRP. But there is some amplification at larger ground motions and at smaller ground motions. So here are the ratios between the new between NGA and the NEHRP factors. And again, this is for a site D ratio. So we're looking at the site D and how you would, if you amplify it using NEHRP versus if you amplify it using the new NGA equations, what are the differences? And so it's NGA over the NEHRP factors. And you can see that in California, for example, there's quite a bit of de-amplification that's taking place, that the new NGA equations are actually not amplifying as much as the NEHRP factors. But as you go up into the Pacific Northwest, there's more amplification taking place at these ground motion levels. And you can see that for both 5 hertz on the left and 1 hertz on the right. So these are just comparing how, when you apply the new NGA attenuation relations, what effect is that going to have compared to using the old standard NEHRP curves? And these are the kinds of effects you're going to see for a D class. Here are some uniform hazard spectra for the Seattle area. For example, on the lower left, you can see, it's difficult to see, but the BC rock represents our old model that we had in 2002. It's the dashed line, black line. The blue and red curves represent how these are amplified as a function of period using the new NGA equations. And you'll have to study that a little bit by looking at that plot, because there's too many details here to talk about. But there are, in many of these cases, you can see that actually the BC rock that we've used now is more similar to a sea soil. That in many of these places, the sea soil actually is similar to what we would have said BC rock was back in 2002. So real quickly, the engineers want to apply a deterministic cap that Charlie's going to talk about in the next talk. And so we have gone through and developed some deterministic hazard models for these caps that are being applied. We selected the files based on weight in the logic tree. We ran deterministic hazard code, and we used exactly the same NGA equations, all with the same weights, to come up with these deterministic ground motions. And then we used the GIS to compare each of the ground motions at each site and select the highest ground motion from each of these different scenarios. And that's what's going to be used in what Charlie's going to present next. Here is an example for 1 second what our deterministic map would look like for the United States. So in conclusion, I just want to say that all this information has been updated. We want to receive the latest information from the science and engineering community that we can to incorporate in these maps. So we will probably start this process in 2 or 3 more years and go through this process where we try to gather all this information again. But when we do that, we really want to build databases and files that people can use and that will be interesting to them. So here's a picture of our website, and you can see that all the information for the U.S. national maps is available on our website, and there's our website shown at the top of the page. We have fault databases there that will define all the faults that we know of, all the parameters that were used. We also have our hazard mapping and analysis tools. One of the most useful ones is our deaggregation website, which shows you which earthquakes are most important at each particular site. There are also probability hazard mapping tools there that you can look at. We have the seismic design values. This is where an engineer can go in and put in their latitude and longitude for a site and get out the design values from any of the IBC or NEHRP codes that you might be interested in. So this is one that's very, very highly used by the engineering community. We also have urban hazard maps, and you can see the urban hazard maps that Art Frankel made for the for the Seattle area. We have scenarios. We're starting to develop scenarios for all areas of the country. From our model, we can look at each of the different scenarios separately and try and understand what the ground shaking would be from each of those. Time-dependent maps, our quaternary fault and full database, and some instructional materials. So if you have any questions about this or comments, we really want to hear them so we can improve this website. But all the information that I've talked about should be available to you on this website, and I hope it's useful to you in the future. Thank you.